Hello, I'm Robert, and this is about problems with NASA's Mars Sample Return Environmental Impact Statement. And NASA is generally, they're very credible, and they're very open with the public. They publish their data as soon as they get it, and they're very open in publication of their images, much more open even than ESA. And they are very credible in their sources and their sites, and they cite things correctly. And I've never seen anything like this draft environmental impact statement from them. So some major lapse in quality control there. The background is that I have been working for several years writing a big paper on the NASA's Mars Sample Return mission and the planetary protection issues connected with it. And I was encouraged by astrobiologists to start this project some years ago to actually write down. I've written blog posts about it, and I was invited to give a talk in a small conference in Oxford a few years ago on planetary protection issues. I haven't actually written any papers on the topic yet. So this is my first big paper that I've been working on for some years now in my spare time. So I can't say that I've read everything in the background. The literature on planetary protection is vast, absolutely huge, on planetary protection for Mars. But I've read the most important sources on the topic. And whoever wrote this don't seem to have read anything. I just show some of the things that are absolutely obvious. You know, if this is not going to stand up for a moment in the courts, if it ever becomes a court case. So these are all the mistakes that they made. You know, they said that Mars life could get to Earth faster and better. So that's a pretty obvious one that I would have thought most people would think intuitively that can't make sense. That Mars life can get to Earth faster and be better protected in a meteorite if an asteroid hits Mars and material gets thrown off, and it eventually hits Earth, reaches Earth maybe even in a few years if it gets there very fast. Then how can it be true that Mars life can get there faster and be better protected than it is in a sample tube that's carefully collected from Mars and sealed with a little bit of the Mars atmosphere and then brought back to Earth? Then how can that be the same as being returned on an asteroid? And for instance, you and I, we are examples of life that could not be transported from Earth to Mars or from Mars to Earth on an asteroid. But of course we couldn't be transported in a sample tube. But if you look at microbes, we have a microbial example that's not that different. So a good example are the invasive diatoms in the Great Lakes. And these cause foul odours and they clog up water treatment plants. And they're not native to the Great Lakes. And there's a similar problem in New Zealand, where they have invasive diatoms that were brought from the northern hemisphere, probably on wet diving gear and things like that. And they're spreading out through the New Zealand lakes, and they're causing major problems there. And they're doing their best to try to control them. And so that's an example of a microbe that couldn't travel across an ocean on Earth. So no way those diatoms would get from Mars to Earth. And you might say, well, of course there are no seas on Mars, but there are these tiny brine, very cold brines. The curiosity is that lots of ideas. There's definitely found salt on Mars. There's the droplets that formed on the Phoenix legs, which was salt falling on top of ice. Creates droplets very quickly, and that's in high latitudes. There isn't ice on the surface where in Jezero crater, but what there are is the nighttime humidity. It gets 100% humid at night on Mars in Jezero crater, nearly 100% in Gale crater. And in Gale crater, Curiosity has discovered that these salts take up the nighttime humidity, and they form little briny seeps of salty water, just temporarily, and then they dry out in the daytime when it's very cold at night, and it gets when it warms up in the daytime, the air gets very dry, and it completely dries out. But for a little while in the morning and the evening, there's these little salty briny puddles, just probably just millimeters thick, but it's like an ocean for an ultra microbacteria, which is 0.1 cubic microns or less. So there are these habitats on Mars, which are not unlike its little salty water habitats in a very dry desert landscape. And then you've got about, from time to time, they manage, over thousands of years, life might be able to manage to get from one to another in the dust storms, kind of protected in a grain of dust or something. It's not too different situation from these diatoms crossing oceans on Earth. That how is that going to get to Earth in a meteorite? We don't have any samples of the dirt or its brines, and if we look at our meteorites, they come from at least 3 meters below the surface on Mars. So you can see intuitively from the very dry southern uplands, where it's extremely cold, it's minus 70 degrees constantly down there, and the air would be very dry, so this whole humidity thing wouldn't work there, not very easily in high uplands. That's where, because the air is so thin, so it's easy to eject to Earth. So you can see that kind of intuitively, that it can't be true. So I'm going to go and there are lots and lots of things like that. There's just one thing and another that they say, that first of all you can see, if you've got the background, you know it's not true, and then you go and check their site, and their site doesn't say what they claim the site says. So I will go through that in a minute, but first of all, I just want to talk about why they did this, and how it could have happened, how this could have passed through NASA's quality control, which is so puzzling. And then I'll talk a little bit more about the actual sites they used and how they miscited them, and why it's so mistaken. What happened in the kind of beneath the hood as to how it went wrong. So first of all, though, I want to say that for people who worry and panic, then this is not of the order of that. It's think of it. It's like, if it's not like setting off outdoor fireworks in your house, which would have a very high risk of setting it on fire. It's much more like, suppose someone was to build your house, and this builder was to say, well, I know officially we're supposed to install smoke detectors, but we're just going to put dummy things that look like smoke detectors and don't really work. And you don't need to put batteries in them, because nobody has ever, there hasn't been any fire in your village for the last century, so you don't need to worry about fire. It's of that order what NASA are doing, just saying, there's no risk here, so we're not going to do anything, basically. And it's quite contradictory, because they sort of say we're going to take precautions, but we don't really need to take precautions, but we're still going to do them out of an abundance of caution, of care, but actually there's no need for any of this. And they're basically like the builders saying, there's no need for a smoke detector, but we're going to put in something that looks a bit like a smoke detector, just because we've got to go through the motions. And so why would they do that? So this is the Margaret Race explains that scientists, this is not responding to this. She said this ages ago in 1996. She predicted this. She says scientists are likely to focus on technical details, mission requirements, engineering details, and the cost. So that's what all they're thinking about. And the general public think about risks and accidents, whether NASA and other institutions can be trusted, worst case scenarios, and whether the methods of handling and containing and quarantine are adequate. So there's no overlap. That's what they're thinking about. That's what we're thinking about in the general public. And there's just no overlap between the two. And these are people who, they wouldn't be trained in ethics or things like that. They've never studied ethics, never studied social issues at all. Probably, like at university, they wouldn't write essays on on politics or ethics or things like that, all through their professional careers focused on doing the engineering and the science. And so it's just their mindset that this is what they've got to do. And you get the impression that this was written by engineers and geologists who just said, oh, we've got to do this thing. And then they just say, well, surely Mars is sterile. It'd be much easier if Mars is sterile. Let's go and look, oh, here, let's do a bunch of sites. Let's add that site on. And that looks as if it might do for this, and that will do there. And it just looks just so hastily put together without even checking if their sites say what they want them to say. So a very clear example. I'll show you. I'm not saying something that is in any way controversial, and this will not survive the courts. If it's ever taken a court case, then it'll just blow apart immediately. There's no way that this could be accepted if it was taken to the courts. And if they maybe hope that it's not going to be taken to the courts, and there's very little publicity given to it, but if it does go all the way through and it was approved as an environmental impact statement and nobody bothered to check their sources, then you get the presidential directive, and that's what will eventually stop this if it doesn't get stopped before. Because the presidential directive, it's made very clear that even if the agency thinks there's no risk at all, still, if anyone is concerned and thinks there could be a risk, the president has to look at it. The president has to organise something to look at it and check it. And as soon as someone starts looking at this with any great care, then it's all going to fall apart because of all these bad sites. So this is the example. I'll just go quickly through the sites in not too much detail. So the natural delivery of Mars materials, you can read the paper my preprint to find out more, and I'll put a link in the description. So they say that the natural delivery of Mars materials can provide better protection, faster transit than the current MSR mission concept, which, as I said, doesn't really make much sense intuitively. How can it be easier to get here on a meteorite than in a sample tube? What they actually are suggesting there, if the method is correct, it's been used, for instance, for the Hayabusa 1 and 2, the Japanese missions returning a sample from an asteroid. And in that case, it was similar to material transferred to Earth through natural processes, so that was correct. That was correctly decided. There was nothing wrong with that decision. But that decision here is wrong. So their first site here, they have a site, they say first, potential Mars microbes will be expected to survive ejection forces and pressure. And they cite to this paper, which you would assume would be about asteroids, microbes being ejected from Mars to Earth. But it's not. It's a paper on the ejection of materials from Mars to its innermost moon, Phobos, not to Earth. And there's big differences between Phobos and Earth. I mean, for one thing, Phobos doesn't have an atmosphere, and NASA don't look at the problem of re-entry into Earth's atmosphere and the fireball of re-entry. They don't mention that there because it's not in the paper they looked at, because Phobos doesn't have an atmosphere. And to get from Martian surface to Phobos requires an escape velocity of 3.8 kilometers per second. That's far less than for Earth. That means there's much less shock of ejection. So this was really the wrong site. And it's not like nobody studied it. There's a vast literature on panspermia and on the possibility of sending materials from Mars to Earth. Lots of papers on the topic. And they don't cite them. And then it's far worse than that. The paper they cite says explicitly that the team did not study sterilization during Mars ejecta formation. The Sterling team did not include any sterilization during Mars ejecta formation in its analysis. And that's their site for saying that potential Mars microbes would be expected to survive ejection forces. Potential would survive ejection forces and pressure. And their site for that says the Sterling team did not include any Mars ejecta formation in sterilization during Mars ejecta formation in its analysis. So this is the pattern. Draft DIS says X, and the site to support X says didn't study X. And this is not what you expect from NASA. It's just very hard to know how it happened. As I say, my engineering mindset seems the best way of understanding it. And then they didn't look at the fireball re-entry because because that wasn't mentioned in that study, presumably. And it's Charles Cockle, and they don't mention, of course, his paper. And he's an astrologist his name is on numerous papers, co-author or lead author or the only author on astrobiology. And he says that the photosynthetic life, he gives this example of Crucochidiopsis, which is Crucochidiopsis is an extraordinary microbe that photosynthetic life microbe has got lots of metabolic pathways, can even survive over 100 meters below the seabed. It's been found there, living there on chemicals and not on light at all. And it can survive anywhere from the harshest, driest, hottest and coldest deserts and to the tropical ponds and reservoirs and seas, and it can survive UV and ionizing radiation, all the same species. And it's called a polyextremophile. And this is one of the top candidates to be able to survive on Mars because it can repair breaks in its DNA. Even if its DNA is just chopped into bits, you can just put it back together again. So really quite an extraordinary species. And by using other copies of it and comparing them and then sticking it all back together. And so Charles Cockle looked at this very resistant organism, and he found that they would be killed by the shock of ejection from Mars. I think just about all of our Mars meteorites, then if there's Crucochidiopsis, the shock of ejection was enough to kill it. It's only at the very, very low end, at about 5 gigapascals, that it could survive. And for instance, I think all the meteorites in our collection, if you go and look at the figures, it's higher than that. 10, 20, it's usually 20, go down to about 15. But theoretically, about 1 in 50 of the rocks that were ejected from Mars would be less than 1 gigapascal. So theoretically it is possible to get here, but it's really quite difficult. And then that's just the start of the process. So so even there at about 5 gigapascals they would be able to survive. But so although it's a strong dispersal filter, that it says that it can be survived even for vegetative phototrophs, so that's like Crucochidiopsis, which doesn't form hardy spores. That's the problem. It doesn't form shock-resistant spores, but it reaches a kind of vegetative, dormant state. And so Crucochidiopsis is not easily, can't survive the shock rejection like some other forms of life that can form these very hardy spores that can survive it much better. And but the big problem with Crucochidiopsis is, do I talk about that here? I should do. Is the fireball re-entry. Also have to be the fireball re-entry, and that's really is the major. The dispersal filter of atmospheric transit, which of course Phobos doesn't have, is the most effective dispersal filter for photosynthesis. That's because if it's photosynthetic life, you'd expect it to be on the outside of a chunk of rock and not be right in the middle of it. And then if it was in the middle and light could get into it, then you expect plasma to get into that through the cracks that let the light in, to let photosynthetic life survive in the center of this rock that supposedly is sent from Mars to Earth. So this fails the most basic fact check, that the natural delivery of Mars materials can provide better protection and faster transit than the current MSR, Mars Sample Return mission concept. And it's just not true, completely false. And then just want to say this bit, that people focus a lot on the capabilities that some microbes might be able to get from Mars to Earth. So bottom line is, we don't have a single example of a microbe from Mars on Earth. It's all theoretical, all based on ideas. We don't know what actually is on Mars. We don't know what kind of biochemistry there is, if there is any life there. We don't know its capabilities. Just like Cucuchiopsis can't withstand shock because its vegetative state isn't like the spores that can withstand shock very easily. Well, we don't even know what Martian life might be like. Maybe it can't withstand shock, even tiny amounts of shock. Who knows? And then what matters is that if there is life that can get from Mars to Earth, what matters is the life that can't get there. So we have the example, for instance, barn swallows. They can get from Europe to United States, say, or Americas, and they can fly across the Atlantic. A tiny little bird, but it's got a lot of endurance. It can fly across the Atlantic. It's got very efficient flight. But the starling can't. And so the barn swallow is not going to be an invasive species in the Americas. But the starling is an invasive species in the Americas. It was brought there by European settlers, and it caused all sorts of problems. It caused millions of dollars of damage in the United States. From things like corroding the roof, like eating the food of cattle, like spreading various diseases, all sorts of things, problems the starling caused that wouldn't have happened if the starling had never got to the Americas. And they just have to live with that now. They can't reverse that. They can't take the starling back again. So in the same way, we need to focus that on the microbes on Mars that have not got here on the meteorite, if any ever have. And those are the ones to be concerned about, not the ones that can get here. So that's just, there's no basis for this at all. So just forget about that, cross that off, that's a mistake. And now here's another mistake that they made. And again, misusing their sites. So they say existing credible evidence suggests the conditions on Mars have not been amenable to supporting life as we know it for millions of years. So if that's true, then why are they even taking any precautions? It's one of these kind of self-contradictory things. But if you go and look at their most recent 2022 site, that's the most recent of all the ones they give. So let's just look at that one, and that says the opposite. And if you go down, it's very, very clear. Let's go and look at my screenshot of the page. And then this is their site. They don't give a page number, but this is the obvious page to look at. And it says, are there chemical, morphological, and physiologic, metabolic, or other biosignatures in currently habitable environments in the solar system? And they say exploration of Venus and Mars, Curiosity and Perseverance, will help establish whether localized habitable regions currently exist within these seemingly uninhabitable worlds. And that is NASA's EIS site for existing credible evidence suggests the conditions on Mars have not been amenable to supporting life as we know it for millions of years. It says the opposite. So this site, this is the pattern here, is EIS says X, site to support X says not X. Just the opposite. And now let's look at another example. The draft EIS says mistakenly that Jezero crater is too inhospitable for life to survive there. Now there are two main issues with this one. So first of all, their site there is a study of Mars special regions, which in the context of planetary protection means a region where terrestrial life might be able to replicate on Mars. So they're looking at the areas where missions to Mars risk introducing terrestrial life. And Rhombotella is not an attempt to explore possible location for extant Martian life returned from Mars. And for instance, those Curiosity brines may be Martian life has different salts inside it, or it's different biochemistry and can withstand lower temperatures. So you can't necessarily say that if terrestrial life can't survive in those Curiosity brines, that Martian life can't. And Rummel itself explicitly say, at present there are no special regions defined by the existence of extant Martian life. And this study concentrates only on the first aspect of the definition. So they don't even consider what extant Martian life could do, because the Martian life because there's no Martian life known yet. So that's one problem with their site. So that's the pattern X, EIS says X, and the site to support X didn't study X and what Martian life could be able to do. But the other thing is, just going back to the same site, it says consensus opinion within the astrobiology scientific community supports the conclusion, and then they cite it to Rommel et al. 2014. What they don't explain is that Rommel et al. It's very serious omission to cite Rommel et al. Without citing the 2015 review, because even while that was in process in the press and being published, ESA and NASA had concerns about it, so they commissioned a review of it even before it was published, and then this review looked at it and was published in 2015 and overturned many of its conclusions and modified other conclusions from this site. And the draft EIS cites Rommel et al. And it doesn't cite the 2015 review, which overturned many of the things it said. And this again is a very serious omission. So EIS says X, and the site does indeed say X. This is about the possibility of it's about looking at being able to tell from orbit whether a particular area of Mars is habitable or not. And that's basically what Rommel was trying to say, et al. in that study. I'm not saying we'd still say it today, but at that time. And the later source, which the draft EIS doesn't cite, corrects X to not X and says, no, we can't tell from orbit whether or not there are microhabitats in Jezero crater. And this led to an omission of any discussion of microhabitats in Jezero crater or spores or propagations that could be brought there in the dust, because Rommel et al. Basically exclude that, and then the 2015 review says actually we don't know, and these are knowledge gaps. It could have microhabitats that can't be detected from orbit, even for terrestrial life, never mind for Martian life. And there could also be spores in the dust that can't be detected at orbit, and the terrestrial life could spread in the dust. So now, here's another one. The draft says mistakenly that the potential environmental impacts from a sample release would not be significant. And in and this is the study that they themselves actually include, the 2009 National Research Council study, says it's simply not possible to discount the possibility that large-scale effects occurred on Earth due to life transferred to Mars in the very distant past. So, in the draft EIS, they say that you would, from my research into the planetary protection, I would have expected a whole long section about the potential environmental impacts of a sample return from Mars and what they're going to do to try and to prevent that happening. And instead, they just say that the extremely low probability of an inadvertent re-entry combined with assessment that samples are unlikely to pose a risk of significant ecological impact support the judgment that potential environmental impacts would not be significant, and then they don't discuss them. That's the end of it. But if you go and look at their 2009 site, this actually says, despite suggestions to the contrary, it is simply not possible, on the basis of current knowledge, to determine whether viable Martian life forms have already delivered to Earth. And then they say, there's no evidence of large-scale or other negative effects attributable to delivery of essentially unaltered Martian rocks, but the possibility of such effects occurred in the distant past cannot be discounted. So in other words, they say that they don't know if Martian life has had large-scale effects on Earth in the very distant past. Recently, it hasn't, but we don't know if it has in the distant past. They don't give an example there, but an obvious example that you could consider is the Great Oxygenation Event. So remember, that was when the photosynthetic life produced lots of oxygen and changed the biochemistry of the oceans and the atmosphere of Earth, which is a very large-scale effect. And there's some the 2 points of view there as to whether it made a previous ecosystem extinct or not. There's some evidence of somewhat larger and chains of, and maybe kind of very primitive, almost multicellular life that could have existed back then. But there's some evidence of just like chains of cells. It's like the very start of multicellular life, as it were. And anaerobes that could have survived before the Great Oxygenation event. So there's some possibility there could have been a mass extinction. Others say no, there wasn't. There's just made very little difference. There's just the anaerobes they used treated. But whatever, whether it was a mass extinction or not, it certainly made a huge difference to our biosphere and the chemistry of the oceans and the chemistry of the atmosphere. And so if we don't know so if photosynthetic life, just to give an example, suppose photosynthetic life originated on Mars and then got to Earth after that, then that could be an example of what they're talking about, a large-scale effect due to microbes from Mars. So they just don't discuss large-scale effects. And I don't mention this list here, but they also don't discuss quarantine, which is a really quite astonishing lapse. The only I mentioned that further down the page in this article, but the only occurrence of the word quarantine, and there's very little occurrence of the word health in their report either. Only occurrence in the word quarantine is in discussion of Apollo missions. The literature that I've studied goes into great detail about quarantine and about the risk of technicians that might be affected by the samples, and they have one discussion of the possible effect of health effects on technicians, but only for technicians who study it in space stations, and they give that as a reason not to return to a space station. They don't look at the possibility of technicians infected on Earth, in a biosafety lab on Earth. They just don't consider what could happen if something went wrong, or if it infected humans if something went wrong during the sample retrieval process. And there's a whole literature about that too. They don't discuss that. It's really quite an extraordinary thing. And and then this is the. Remember I talked about how they cited the 2014 study, but not the 2015 study. Well, it's another example. They omitted the 2012 European Space Foundation study, which reduced the size limit to 0.05 microns and they said that a particle larger than 0.05 microns and larger shouldn't escape the building the facility under any circumstances. They reduced it. So this is the site they used, the 2009 one, which I was just talking about a bit earlier, and that had 0.25 microns. Oh, I've got a semicolon there. Change that to full stop. And this was reduced to 0.05 microns in just 3 years. So that's and this was due to. And let's just have a little look at this. And let's look at the evidence they used. So this was this is not the actual evidence. This photograph has been taken since then. But this is to 0.2 microns. These are 0.1 micron things. The National Research Council said that it's okay to contain them up to this size, 0.25 microns. And the European Space Foundation said, well, actually, in the 3 years since you made that decision, they found that microbes can get through these tiny holes. And then later on, they actually took scanning electron microscope images of them. You can see how they're narrower than 0.1 microns. And as a result of that, the European Space Foundation set a limit of 0.05 microns. And they said that the draft EIS says, yes, so the draft EIS is not. It's going to use. That's why they say it. Unacceptable 0.05 microns. Upwards, they say is unacceptable. The release of a particle larger than 0.05 microns in diameter is not acceptable in any circumstances. That's a screenshot from it. And then here it is in text as well. And NASA are completely unaware of this. And this also shows that NASA didn't respond didn't read my comment. Now my comment my comment this time, I made the comment very early on, so it's on the first page of results. So there's a chance they might read it this time, but they clearly didn't read it last time, because Aman et al. Isn't in their list of sites, list of references. They don't refer to the European Space Foundation study anywhere in the draft EIS. It's just not there. And I said in my comment, so if I go and look up and now and find the bit that I said, let's search for, let's go and find a bit where I talk about that. There we are. This is what my first sentence in my comment in May said, are you aware of the ESF Mars Self-Return Study? And I gave the reference and page numbers, where it said the release of a single unstellar particle larger than 0.05 microns is not acceptable under any circumstances, and I explained why. This contained starvation limit ultramicron bacteria which passed through 0.1 micron filters, and I gave the site to that evidence, and that is well beyond the capabilities of BSL-4 facilities, and even Alpha level 17 filters can't do that, and they just don't seem to be aware of that. And so I can confirm that they didn't. They haven't emailed me. They haven't contacted me. There's nothing in the EIS to explain why they don't include this site. They don't say that there's some reason why the European Space Foundation. The European Space Foundation is as reputable as the National Research Council. There's no reason to exclude a major study by the European Space Foundation. And they don't give a rationale. They don't say somewhere, well, actually the European Space Foundation study is not reliable because X, Y, Z, there's something you didn't understand or something. They just don't cite them. So this shows two things. It shows that that whoever did it, they just weren't aware of the literature on the topic. Maybe because it's in Europe, I don't know, and not in the United States. And it also shows that they don't read the comments. So they may have read the first few comments, but they obviously didn't get as far as my one, because they then didn't respond to it. And they actually have a section in the EIS where they respond to comments from the public, and they don't mention this issue. So it's clear that they're not responding to comments. And it's now, so now what's going to, let's just quickly go up to the top and look again at, I've got to quickly go, maybe that's enough to, those are the main things. Is there anything that I've left out about all this? I think I've gone through all of them now, actually, of the most important ones, the large scale impacts. Yeah, I've gone through everything. So, so I'm just going to talk about that and then this bit, and I'll leave the rest for either some other video or whatever. So I just want to talk about alternatives, but first of all, what is going to happen in the courts if we do all, as a result of all this? Yeah, oh, that was my thing, that was just that. And so, so it's my understanding that it's likely that if this gets to the courts, that the justice will grant an injunction to pause the entire project for the duration of the court case. And then, if litigation succeeds, that they have two options. They refer them back to the agency, and they can refer them back with an injunction, which is to say that everything's got to be sterilised, or they could refer them back and just tell them to stop the project. So I'm not a lawyer, and I welcome input from legal experts on what would actually happen. But the courts have quite a bit of clout here. So and I say that'd be a great shame if they just stopped it. But if they do keep pushing through with it, I mean, I personally would support taking out a court case on this. But you know, try to ensure that the court case is done the right way, and that it's not telling you to just stop it altogether, which is a risk. If it may be better to actually do a court case that is well informed than to wait for someone to do a court case that is ill informed and just try to stop it altogether, which they might well succeed at. So, my concern isn't that the mission will go ahead and not be safe. I can't see it getting anywhere really. But of course, there's a presidential directive, even if it isn't challenged in the courts. But it's a risk of the public responses. If you look at the public responses, so loads of people, even all the people, just everyone who responds to it, just nearly everyone, with just a few exceptions, is saying this is dangerous, or don't return to Earth, or test first. Generally everyone is saying one of those things. And this is clearly going to be the way it's going to continue. If as the mission continues and as people become more and more aware that this is what's going on, it's not going to go away. The public aren't going to stop being concerned because NASA manages to get their environmental impact statement passed through. That's not going to happen. So that's just trying to bury the problem. It's going to come up at some point. Rommel said that. He said anyway that we need to have a former planetary protection officer from NASA. He said that the public needs to be behind it, because if not, then it's essential for the success of the mission to have the public on board. It's just going to fail if they don't do that. So the other thing that they've done is that they only have two options: no action, or it being handled in a safety level 4 facility. I didn't explain that the technology doesn't yet exist to contain 0.05 micron ultramicrobacteria or nanobes. We don't have that technology. It's I looked through literature. I found one paper which showed 100% success in containing polioviruses, which are small enough to meet this standard, and some other very small viruses in water under high pressure with silver doped nanotubes, nanopores, which is really quite hard to maintain. I found nothing that could do that with the air. I found a filter that could contain coronaviruses and COVID. So the containing droplets is what most people are focused at, but this is looking at individual coronaviruses. And if you go down to individual coronaviruses, you can't do that in the air. You can achieve 88% reduction. That's the best they managed with an experimental 6-layer filter. And so the requirements of the European Space Foundation just can't be met with current technology a decade later. And it's not clear that even a decade from now we will have this technology. If that's true, then we can't even construct a lab on Earth that would be able to handle these samples, according to the European Space Foundation studies limits. Clearly, NASA, if they are going to go ahead, I think that there's no doubt about it. NASA have to stop this EIS. It's totally not fit for purpose. It has to have a complete restart. They have to bring the public on board. They have to do a review of the size limits before they even think about starting again, because that 0.05 microns is not necessarily the minimum. There's lots of research on these theoretical ribocells, which would be far smaller, and it might be that 0.05 goes down to 0.01. If the ribocells are considered to be a viable possibility for past life. And now with the new research, there's been lots of new research on ribocells, which are cells without proteins and just RNA and without DNA. That can be very much smaller, and they have little chunks of RNA crisscrossing with each other to act as enzymes. And so you get very, very small, slow-acting enzymes, but if there's not much competition, then it would be able to replicate very slowly and very clumsily. And that's a possible thing that we might find on Mars. So, and if it was mirror life, it could be quite serious, returning mirror nanobes. So so they looked at they only had no action. They looked at these other possibilities and they just said no, 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 of conducting the analysis elsewhere, basically on the basis that it makes much more engineering sense to return it to Earth. That's basically their approach there. They need to include 100% safe alternatives. And the simplest one is sterilization. That if the present-day life is unlikely in the samples, and if past life samples are seriously degraded already by exposure to cosmic surface radiation, then the X-radiation sterilized is not going to impact on geological studies. And it's like, if there's any life, it'll be recognizable by astrobiologists, but astrobiologists don't really expect to find anything much of interest in the samples, as the mission is at present. So, because it's designed around geology, again, it's the engineering and geological mindset. So what they did is the engineers were concerned that if they were to completely sterilize the sample tubes and remove all organics from them, they would then have to enclose them in some kind of container, because as soon as they open to the atmosphere, they get recontaminated. And then, so if they were to put that then on the spacecraft, it can only be opened in space. So that would be an extra failure point, and engineers are always trying to eliminate failure points. That would be a mission critical failure point if the container didn't open for returning samples from Mars. So they said, well, we're not going to do that. So instead they cleaned the sample tubes as well as they possibly could. But what seems like a very clean samples from the point of view of geology, and if you're looking at like trace elements for habitability of past Mars, it'd be another habitability thing, which is what they focus on as geologists, because that's nothing to do with whether there's actually life there. But the amount that if you look at the ultramicrobacteria, you can get 10,000 of those to a nanogram. If you look at the theoretical ribocell that I was talking about, you could get 20 million of those to a nanogram. And they permitted 8.1 nanograms per tube of organics, and 0.7 nanograms for each biosignature. So that's 7,000 ultramicrobacteria equivalent of each biosignature. Take a particular amino acid, then they would permit enough of that amino acid to completely fill 7,000 ultramicrobacteria, and you'd hardly, if you had 1,000 ultramicrobacteria worth of just a single amino acid, then you wouldn't notice. And of course, a lot of the inside of an ultramicrobacteria consists of water. So this is just, unless there's extremely abundant life in these samples, which is not credible, because the surface geology is ionizing radiation is going to erase biosignatures. What ionizing radiation does, it can split it completely up into gases and water vapor and carbon dioxide. It can cause things to reconnect, so that the bonds break and then they become reactive and they stick together in a different way. And so this has been going on the surface of Mars from cosmic radiation, and over hundreds of millions and billions of years, the biosignatures of the past are just completely unrecognizable. So the astrobiologists have said that it's absolutely essential that two things you have to do. For past life, you have to be able to drill below the surface to get to it, and then you have to be able to look for life in situ. Because the other thing about life is that past life on Mars, then it's likely to be what they call heterogeneous. It's very patchy. So if you look at the worst case scenario for past life on Mars, we're talking about 3 billion years ago. We're talking about a time when, long before photosynthesis on Earth, there mightn't have been any photosynthesis on Mars. There might have been nitrogen fixation. It might have been, indeed, if you look at the worst case scenario, perhaps life was still just living around hydrothermal vents, and perhaps even just a particular hydrothermal vent, and it hadn't yet developed the ability to travel to another one. That'd be a very worst case scenario. But you can see from that, be anything between that to, it can survive, but only in some habitats, not in others. And it might be it just can't survive in Jezero Crater, but it might be it can in the delta in some particular habitats. And then you have to trying to get it through to the present. Then if you look at the delta, then okay, you likely have lots of life in the delta if you have photosynthetic life, or especially if it did have photosynthetic life back then. But in some places in the delta it's being deposited, in other places it's being eroded. So if you're looking for life, you need to know, it depends on the particular currents that were there billions of years ago as to whether you were likely to return life from that particular sample. It's very unlike geology. And then there's the question about, if it's been deposited, was it on the surface maybe for a few 100 million years at some point in its past history? Then the biosignature would be erased. Was there something came through that the water came through that washed out the biosignatures? Was there some like chlorides or perchlorates or hydrogen peroxide or something got into? There's lots of that stuff on Mars that would erase the biosignatures, and lots of things would erase it, and then it has to be returned to the surface very quickly in the present. Within a few tens, 100,000 years would be far the best. So since Perseverance, this is why I give the analogy that it's a bit like, if you look at it from the point of view of a geologist, imagine that you could get a rock collection back from Mars, and you say, oh super, great, I still wanted to get a rock collection from Mars. But now they spring the gotcha at you that actually we don't know for sure if there are any rocks in this rock collection. And also, what we do know for sure is there are lots of rocks from Earth that are in this rock collection. We don't know if there are any Martian rocks in it. There might be a few Martian rocks amongst all the other rocks, because we sent a big collection of rocks from Earth to Mars. Then we tried to pick up some rocks from Mars, but we don't know if we managed to get any. And we returned this huge collection of a mixture of rocks from Earth and possibly a few rocks from Mars. And there's no way of knowing which of the rocks come from Mars and which come from Earth. And how are you going to do your geology? That's basically the situation an astrobiologist will be with these samples. And so astrobiologists really, they wouldn't be that bothered if it was sterilised, because it's extremely unlikely to have life in it. And then geologists aren't bothered about sterilisation because they say, can they do geology with sterilised samples? So the simplest answer here is just to sterilize the whole thing, and I acknowledge that it's just a technology demo for astrobiology. So that's 100% safe for Earth. You can design ways of sterilizing it during the journey back from Mars, or you can collect it in a satellite in above Earth orbit and sterilize it here before returning anything back to Earth. So they should include this as an example, as a no action possibility. So now I've got another idea though, which is we could make it much more interesting. So first of all, if it's going to be interesting to astrobiology, we've got to send 100% sterile containers to go to Mars to return a sample of dirt and a highly compressed sample of gas from the atmosphere. So these are the things that were dropped from Perseverance. So people were saying, we want to get some dirt, we want to get some gas, we want to get some dust from Mars. And the geologists look at that and say, well, those aren't rocks and they're not terribly relevant to geology, and they just drop them. And there will be some atmosphere, but atmosphere in the sample tube where it's not carefully collected, and there'll be evolved gases from the sample tube. It's not really much of a sample. And so we can make it hugely much more interesting to astrobiology by putting these descoped things back into the mission, and we can still do that using the orbital sample container. So this is a few grams of dust. So I talk a little bit about this. This is how we can manage to do that. This is a tiny thing. We're not talking about a big thing. Joukowsky-Styles idea. So we have a MOXIE on Mars, which is compressing carbon dioxide from the atmosphere, and then it splits it up to make oxygen, and then it just then releases it into the Mars atmosphere. It's no point. It's not a sample return experiment. They just put it on Perseverance because the enthusiasts for humans on Mars want to send this on some mission to Mars, and this is for making fuel on Mars, so that you can go travel around it in rockets. And so this experiment has got a compressor in order to compress the CO2 from the Mars atmosphere, and which it then turns into oxygen. Well, Joukowsky et al. Said, well, we've now got a compressor that's been tested that works on Mars, so let's use that to compress a sample of atmosphere and return that. And to do it properly, so the whole thing would be sterilized, or you'd want to sterilize it especially if it's biological. You have your gas reservoir, and the compressor first of all pushes gas through the gas reservoir into a getter. That's to get rid of any traces of gases on the walls of the reservoir, so they get evolved off. And then it compresses the air, and you can fill a gas reservoir. And if you take the largest thing for 100 cc's, then you can compress that to 100 litres and a fifth of a gram of Martian atmosphere, and that's enough to start detecting very sensitive measurements of trace gases of biological interest. So that's purely, that is a biological interest by itself. And then if there is present day life on Mars, there's some question about like the methane signals and so on, whether any of that is due to life. There might be enough life to cause very trace effects in the Mars atmosphere. And then once that is finished, you then run it in a different cycle. You close that microvalve. You close that one after you've got the getter. You close that one after you've filled the gas reserve. You open this one, which enters the atmosphere, and then you continue compressing, but the aim is to gather lots of dust into the dust filter. And you just clog up that dust filter completely with dust, and then that gets you your dust sample. And ideally you'd want to run that during dust storms. So because that's a time when, if there's any life, it might even be triggered to produce spores during dust storms. Who knows, or propagules? But that's the time when you're more likely to get less degraded cells from distant parts of Mars. And so many people may not know this, but you can, for instance, detect life from the Gobi Desert in Japan. The microbial life, spores, propagules, little bits of life from the Gobi Desert. So you could get evidence of, you get a first idea if there's two camps of astrobiologists, something there's almost hardly any life on the surface of Mars, something that is that there might be life almost everywhere in very small quantities. No, none of them think it's very abundant on Mars, not like Earth, but there could be microbes almost everywhere, just to like a few to a gram or something, which is very small numbers for microbial life. Well, if we do this experiment and collect the dust, and if there is a distant habitat, especially near Gale Crater, but even a very distant one that's quite productive of life, then you would expect to find some cells in the dust. So let's give a first upper bound on how much life there is on Mars. If we don't return any life, then we will know that it's really quite rare on Mars, which is useful first bit of information to know. And if we decide a little bit between these two groups of astrobiologists to some extent, you start the rarer habitats are more likely, or there's some reason it's not getting to the surface very easily. Maybe even it's just below the surface of rocks or something, but for some reason it's not either not very much of it, or it's not getting spread very well. So that would be of astrobiological interest to do this. It's also interest to potential astronauts, if we ever send astronauts there, because we want to know the dust. We know the perchlorates in the dust, and maybe other nasty surprises, including life, of course. So that's that idea. And then the other thing of great interest to astrobiology is to scoop up an extra sample of dirt, like the Viking scoop. So Viking scooped up this dirt. That's it. That's its scoop, and it got really it got these intriguing results that nobody's really properly explained. Many people think it's chemistry. Other people think that it is complex. That it is biology. If it is chemistry, it's very complex because you get what looks like a circadian rhythm. So what happened is a very simple experiment conceptually. They fed radioactive organics to the soil, and then they looked for evolved gases. They didn't test what it was, whether it was methane or carbon dioxide. We're talking about quite early experiments back then, when you just couldn't fit something good analysed to that degree very easily into an experiment. So they spotted the radioactivity of the evolved gases, and the evolved gases, they did produce gases just like life would be expected to do, but this could be due to chemistry, which they didn't know about the perchlorides. They didn't know about how reactive the chemistry was on the surface of Mars. But what is interesting is that the peak of the evolved gases is offset by 2 hours, happens 2 hours later than the warm. So it's not designed to get warmer and colder, it just went warmer and colder due to the variation in the Mars surface temperature. And when it was warm, then about 2 hours later, that's when the evolved gases peak. And that's very hard to explain, apparently, according to chemistry. And it's a very common thing to happen with life. So we either have very complex chemistry there, or perhaps there's life. Perhaps there's life in these curiosity brines, for instance. Or perhaps they're just spores spread in the dust that can still be viable, that Viking dug up and brought to its sample, it's brought to its experiment. So this is something that we need to know the answer for. If it's life, then bingo, we get paid that. We get we get extraordinary results. That we find out what life is on Mars and what it is. If it's not life, then we get to learn about this complex chemistry, so we can discount for it in the future. For future life experiments, we know what to look for on Mars, and we're not going to get fooled by whatever it is that caused these strange results. So either way, astrobiologists want to know what's in the dirt on Mars. And generally for life, you're much more interested in dirt than you are in, well, it depends, but especially on Mars, the dirt is where it's at. You really want to know something about the dirt on Mars if you're going to if you're doing astrobiology there. And the dirt is very interesting on Earth as well, of course, for anything biological. So that would be a top priority. So my suggestion is that the NASA, in the draft EIS, they talk about how the idea of returning it to a laboratory above to a safe place not connected to Earth, that if you kind of take the sample tubes, open them up, and take samples down to Earth and close them again, then all that would cause all sorts of problems and contamination, make them harder to analyse and so on. So what I suggest is that since the astrobiologists are really not that interested in these geological samples, because they are geological samples, and okay, let the geologists study them and find out about past habitability, and they've got the low enough levels of organics for that. But what the astrobiologists are interested in would be these extra samples. So why not send the geological samples, thoroughly sterilise them, send them back to Earth, and then take these extra samples of this high interest to astrobiology, keep those in, collect those in sterile containers, and send them to somewhere safe, which is not connected to Earth, and they're not sterilised. And so that is my suggestion. So this would be the second possibility. That's just about how you could collect the dirt in the next little bit of the sample return. This is the sample container that they're hoping to return, a first idea about how it would look. You could have like a plate on top of it and a little pile of dirt, but in reality it would be a sterile container, and the astrobiologists would think it's worth the risk of not being able to open the container to actually collect it in a sterile container, to send a container to Mars to put it in. So that would be the astrobiologists taking on that risk for their particular part of the mission, and it's not going to affect the geology. it's not going to cause any problems to geology if the astrobiologists get to Mars and they can't open their container. So this is the second possibility. Let's go and have a look at it. There's my graphical abstract. And so in this idea, what you do is that the humans never go near the satellite, so it gets returned to a satellite above geostationary Earth orbit. There's a particular orbit that is very safe, even if you get the spacecraft exploding, then little bits would still be in stable orbits in a particular orbit I suggest called the Laplace plane. And so, perhaps 10,000, 20,000 kilometers above geostationary Earth orbit, no possibility of being of affecting geostationary satellites either. And so the samples stay there. There's no risk to the Earth's biosphere, and astrobiologists, they send things from Earth to the satellite to study it, and then they might return things from the satellite to Earth at some point, but they take a little bit of the dust and maybe take it back to Earth, but they would sterilize it before doing that, unless they're absolutely sure what's in it. And they would study it, so we have, just as they want to send these in situ instruments, as I said, to go to Mars, they want to send instruments to go to Mars, to go here, there and everywhere looking for life, see if they can find it. And then once they find it, then that's what's to be returned to Earth. That's what they want to do with past life and present day life. They want to, like, metaphorically go and look for the rocks from Earth, from Mars on Mars, if you look at the geological point of view, geological analog. So the astrobiologists would use these same miniature detectors they've already designed, and some have even been shown to be flight worthy, but just been descoped because the geologists said, well, but this doesn't look like it's going to be terribly interesting. And so these instruments are all ready to send up to geostationary Earth orbit, and we can send multi-ton things to geostationary Earth orbit now. And when you get to 2030s, which is when these would return, you could send even bigger things up to geostationary Earth orbit, probably tens of tons in one load. So they can send lots of instruments up there to study these samples, and then and as long as it's just going in the forward direction, it's not going to cause any problems to Earth. And then anything comes back has to be carefully sterilized unless they know it's safe. And so in that way, the astrobiologists then can study it remotely from Earth, just like driving a rover around on Mars. And they just have sample telerobotics. They move things around, but with much, much less latency than on Mars. So this is my second 100% safe alternative. So I think that NASA should include these two options of 100% sterilized and sterilized above, and sterilizing the geological samples while taking extra samples of interest to astrobiology to return to a safe orbit above geostationary Earth orbit. And I think they should look at those two, and I think it's particularly adding this extra samples will actually increase the science interest over what they have already, greatly increase it. So we're talking about increasing the science interest by this second alternative for astrobiology. There is and then I'll just briefly mention. Oh yes, this is about. I talk about quarantine. People talk about returning it to an orbital station with human technicians, but this wouldn't work. So this is something that's new to my that's new to my paper. I'm not sure that there's been so much attention to this, but I certainly don't know anyone who's used this particular example. But if you look at there's the example of the zinnia plants, which they grew on the ISS, and you may, if you follow the space news, you probably come across it, that 2 of the 4 infected plants died. They found out that it was a mold that got to the International Space Station on a human microbiome. So the humans, astronauts, they wait and they quarantine for a while so as not to bring any colds to or flu or COVID or whatever to the International Space Station. But they don't quarantine against molds that can affect plants, because you can't, because molds don't affect humans, except this one does. This particular mold can affect immunocompromised, and in some situations this mold can harm humans. So that's another example that if you had a mold on an astronaut that could harm humans but doesn't harm that particular astronaut, then that's another way that you could get life from Mars that is actually harmful to humans but not that particular astronaut. You can have the equivalent of what's her name again? Typhoid Mary, who had typhoid, but she didn't have any symptoms. So you can have a symptomless carrier of disease. So an astronaut could bring things out of quarantine that are harmful to other humans, but not to them particularly, because of something special about their particular makeup of their body. And they can also carry diseases of plants, and they could also carry mirror life. So that is the worst case scenario. So there are lots of scenarios that could be, life from Mars could be beneficial to terrestrial life. So, and it could make no difference. It could also be harmful. We don't know until we find out what's there. But quarantine just can't work. There's no way that you can protect Earth from Martian life with human quarantine, because many things that could be harmful to Earth would do absolutely nothing to humans. You wouldn't notice any symptoms, and then there's no way of sterilizing the human microbiome, and so there's no way of preventing it from coming back to Earth. So I have a section about that in here. You can have a read about. And then this is the idea of mirror life that I talked about, mirror microalgae. Then if those got into our skin, you shared in the microbiome, one example for some children, they released 40 million bacteria and 40 million fungal spores per child per hour. So if something like that became part of the human microbiome, there's just no way to contain it. So that's why we can't deal with this by handling the samples with humans, technicians in an orbital laboratory, and using quarantine. That's not going to work. It's also not going to work with technicians handling the samples on Earth, because if you have technician handling it, then you get a leak, and the technician is exposed to the samples. There's no way to isolate that technician unless you isolate them for their entire life, to be sure that they're not going to bring whatever it is harmful to Earth. Yeah, I'll give the example of Typhoid Mary, who had to stay in isolation for the rest of her life. So the microbe, mirror life could be harmless to humans in orbit, take part in the human microbiome, not even notice amongst all the other microbes, but when we return to Earth, it enters the oceans, gradually adapts and spreads. And then the thing is that any mirror life on Mars would be already adapted to eat ordinary life, to metabolize ordinary life, because that gets there in ordinary organics, not mirror organics, because that gets there via meteorite impacts, via comets, via interplanetary dust. And it would gradually turn all organics on Earth into mirror organics. And then humans, this would happen very slowly. Humans wouldn't go extinct in this scenario, not with modern technology. Very slowly, over years, decades, and eventually centuries, all the organics on Earth would become mirror organics. All of our ecosystems would probably eventually fail, because the plants and animals wouldn't be able to make use of mirror organics. And then we would probably be able to preserve maybe most or nearly all of them in biomes that we would gradually construct that would cover eventually the whole planet and much of the sea, in order to preserve present day life. So, but it would be severely degraded. So we don't want to return mirror life from Mars, not unless we can prove that's not going to happen. So this is an example of worst case scenario. This again is not, it's not peer reviewed, but it's pretty obvious. It's just putting two things together that astrologists agree that we don't know what form of biochemistry there is on Mars, and it is possible to have independent evolution on Mars. They designed the instruments to look for independent evolution, and then it just joins that together with, and mirror life is a possibility, and some people say it's the 50 just luck of the draw. And then the final thing it gets together are what the researchers are trying to flip ordinary life into mirror life. In the laboratory, they would do it to make sure it's safe, to make sure the laboratory life is dependent on things in the laboratory. This is going to take a decade or more maybe to finally achieve it. They will make sure that if they do produce mirror life in the laboratory, it's dependent on chemicals that means that it can only survive in the laboratory. But they have talked about what would go wrong if mirror life could spread throughout Earth. So combining those three things together, then you get this scenario. And so, so this is something we've just got to bear in mind. That this is a possibility. It's not a foregone conclusion that Martian life is safe for Earth. It may very well be. There are lots of ways that it could just be beneficial or harmless, but we don't know until we study it. I talked about that. So yeah, it's just a little look down. So this is my third alternative, and this is something for engineers to look at, which is this sketch. So we do know how to return. We can return a sample in a titanium sphere. That would be totally safe. So if you take a sphere, then when it goes through the atmosphere, it doesn't burn up. This is actually returned to Earth. That's an example of a sphere that fell from the sky, and it's, as you can see, it's undamaged, because that shape slows down very quickly, and then titanium melts to a very high melting point. And so we could return a sample in a titanium sphere, and it would be totally safe. But then how do you get inside? How do you then study something that's inside the titanium sphere, and what's the point? You could even do end-of-mission sterilization, heat up the titanium sphere, and then it's sterile, and then you could open it. But how do you look inside when it's not sterilized? Well, so this was my idea. I haven't come across anyone else look at it, and the idea is to not have air between the two, but have a sump of vacuum-stable light oil, which the vacuum stable is just because it means it doesn't evaporate even if it's very hot. And it's at 300 degrees and high temperature. This is used for space applications. It's called pentane X2000 oil. And so that will be kept at a high temperature. You get the sample in there inside your tube, inside your sphere, safely returned. The entire laboratory is built inside an oven, because you've got to, if you're going to do this properly, you've got to consider the end of the lifetime of the facility. Once, at some point, your facility is going to be demolished or something's going to happen to it, you've got to make sure that the whole thing can be decontaminated at the end of the lifetime. But you're talking about the possibility of something like mirror life. So you build the whole thing inside an oven, beneath inside a former nuclear bunker. So this would be quite an expensive thing, but it could be worth doing in the future, especially if we find that there is life on other planets and we want to study it on Earth. Then and it turns out to be completely unsafe. We can't return it safely, like mirror life. Then maybe at some point we will construct something like this, so we can actually return it safely to Earth. And then we'll go through the sump. The sump would be is to just make no air can get through, no nanos can get through, and the sump would be full of cobalt, radioactive cobalt, which would ionizing source. So anything gets through there gets totally sterilized. And at high temperature, 300 degrees centigrade, then it's a fail safe, you can heat the whole thing up to 300 degrees centigrade if something goes wrong, and just to sterilize the whole thing. Inartly, sump, everything, the whole thing would just be heated up. You lock it all up and heat it, and just keep it to 300 degrees centigrade for a month, and then there'd be no life left inside. So that's my sketch. I'd be interested if engineers to have a look and see if it would work. But it seems to me that it could be possible, even with the European Space Foundation studies limits, and even if you go to 0.02, 0.01 micron, that this would still work. It doesn't matter what size the life is. It would still be possible, in principle, to return it to Earth. So I suggest that NASA could look at other at 100% safe options for returning it to Earth as well. It'd probably turn out they say, oh, well, it's far too expensive, but they could have a look at it and see you just examine it, and it could probably, but once you've got the principle that it can be done, then there may be ways of reducing the cost, so it doesn't cost as much as this hugely expensive thing that I've just described, and that would still be 100% effective, and doesn't depend on filters to protect, but sumps instead, or something like that. So anyway, that's it. So I could talk about many more things. You can look at my blog, my link in the video description. I'm considering doing probably going to do a blog post about this, and I thought I'd do a video for it all. And so I hope it helps you understand the background here, and do go and comment on their draft, their environmental impact statements. Say whatever your own personal views about it. What do you think they should do and shouldn't do, and what you think about the whole thing. But I thought I should do this because most people don't have the background that I have of having read the literature on the topic, and so this analysis that I just done for you, most people wouldn't know how to do that, and it's because I've been working on this paper on the topic for the last several years on this entire topic of planetary protection for the NASA Mars Sample Return mission, and that's why I have the background that made it possible for me to do this. And as I say, I could get together really quite quickly because I got all the sources and all the work already in my larger paper, which goes into some various other things. So it was just a case of a lot of it was kind of copying things over and then checking the sites and then writing it up and so on. And I could probably do this as quick as anyone really to get something like this together. So this is not past peer review. So I'm not asking anyone to say, well, because Robert said it, that therefore that's correct. Because remember, it hasn't been peer reviewed. But these things are just so obvious that I think. Let's just end with that, the call for action. So I'm not quite sure how to take this next, what we're going to do. I don't think NASA is just going to stop doing this because of my comments telling them to stop, my most recent comment I just submitted today says, you should stop this and start again. And it explains a bit what I've said here. Now, I might upload the new comment link to this video. I don't know. I can embed this video in this paper, draft paper, and then anyone who reads and then upload as a final version. This is my call for action, but this may get changed as a result. I plan now to try and contact the top quality, the leading astrobiologists and planetary protection experts and so on, and ask what they think about all this. So I haven't done that yet as of giving this video, but this is what I suggest, that we could have a letter like this, which we could maybe upload to the as a comment for these public comments, a letter from top astrobiologists, if they're willing to sign it. And so it would say that first of all, call NASA to fix the inaccurate sites, to bring up the standard of a peer-reviewed paper in Natural Nature or Astrobiology, and add the missing sites, those two missing sites I mentioned. That's the one about the 0.01 micron, 0.05 microns. And that's the one about the dust storms and microhabitats. And so I'm not saying that NASA should listen to what I said about that, but it's clear that it needs peer review, and these peer reviewers would then look at it and say, and they would look at this, I'm confident that they would see the same problems that I've seen, and many more probably. And so the peer review needs to be done by astrobiologists of high standing that are not directly involved in planning it, former planetary protection officers and members of the boards that carried out the ESF and NRC sample return studies, and it should include those. I don't want to make that exclusive. And then add alternatives to no action that keep Earth 100% safe. Like I was talking about those three alternatives that they need to add. And then I've got this warning that quarantine won't protect humans in a space station or laboratory, which I think is pretty clear. I've passed this run this past all the experts that they're willing to sign to that as well, and ask for the alternative actions to include 1, sterilising all samples, and 2, return unsterile samples to safe orbit above GEO, and return sterilised samples immediately. So those 2 options, and that NASA could look at other ones as well, of course. And then we also call, so this, we'll see what the astrobiologists say about this. I expect them to agree. We call on NASA and ESA to add capabilities to return samples of dust, atmosphere and dirt. And they're returning 100% sterile containers with no traces of terrestrial biosignatures. Then we call, before the next draft EIS is submitted, so just stop this one altogether, it's not fit for purpose. And unless the decision is already made to keep Earth 100% safe, then call NASA to initiate an exercise limits review that was mandated in the SF report. And then once the size limit is reviewed and they know what they have to do, call them to start an investigation of whether the technology to achieve it exists or can be developed in time to be useful. As far as I can tell, it doesn't exist yet, and I'm not clear at all if it can be developed. They need to investigate that. And then whatever decision is made, we call on NASA to set up the recommended planning and oversight agency, such as many people have recommended should be done, and open to representatives from all people. And that's necessary even if the decision is made to keep Earth 100% safe through sterilisation of all samples. We still have the problem that the public may not understand that it is safe. And as Rommel et al. Wrote, broad acceptance at both lay public and scientific levels is essential to the overall success of this research effort. If they don't do that, then this is a huge risk of just not succeeding, of the general public kind of being, including conspiracy theories and all sorts of things that people worry about, and just lots of protests and people saying this must not be returned, even if it was totally safe. That could happen then as well. So we just need to have broad acceptance of the general public and understanding, and ask them to NASA only resubmit the new EIS after the NASA's actions are well understood and accepted internationally. Not do what they're doing at the moment, which is nobody even knows about it, and the ones who are commenting on it, they're saying that it's dangerous, don't return it, or test first, and that's totally unacceptable. They've got to have an atmosphere of broad understanding amongst the general public about what's going on. I mean, they don't have to convince every eccentric, but some broad understanding that this is what's going on. And so we don't think it's acceptable to continue with this EIS until NASA's actions are more widely accepted. So that is my draft letter. And if you've got any thoughts about how to handle this, I'm very, very interested in any ideas you might have about what we can do about all this. So I'm very interested in any comments on this. So I'll now stop this recording. I'll upload this, put it on my YouTube channel for Mars and space colonization things, and I think I'll do a blog post about this, and I'm going to start emailing these top astrobiologists and other contacts, and there's some that I've had email correspondence with, just very brief email correspondence, and others that I've never tried to contact, and I'll just kind of try everything I can to try and get this sorted out, because I think the public deserve better, and it's really important to do this properly. It's also very important as a precedent, because the United States tend to be followed by other countries. So if NASA don't take precautions, then China, Russia, once they're going back in space again, Saudi Arabia and so on, they would copy what NASA does, and they'd be sending missions to Mars without these metaphorical smoke detectors and bringing back dirt from here, there and everywhere, bringing back all sorts of things from Mars, and just not taking precautions except on BSL-4, which is totally inadequate. And so So I think it's really important to do this right, and so that's what this video is about.